100 years ago, a man made a prediction so radical that many scientists struggled to believe it. And today, we can actually see the proof. He said that space itself could bend. That time could slow down. That the very fabric of reality was not the rigid, fixed stage that science had assumed for 200 years, but something dynamic, flexible, warpable. He was right about all of it. To understand why Einstein's ideas were so revolutionary and so controversial, you first need to understand what the world believed before him. For over 2 centuries, the universe ran on Isaac Newton's rules. His theory of gravity, published in 1687, was one of the greatest intellectual achievements in human history. Simple, elegant, devastatingly accurate. Newton said every object with mass pulls every other object with mass toward it, across the vast emptiness of space. His equations assumed gravity acted instantly across space, invisibly, and perfectly. With Newton's equations, scientists could predict where a cannonball would land, when a comet would return, and even discover planets no one had ever seen, simply by watching the gravitational wobble in neighboring planets. They used his math to map the solar system, to navigate the seas, to launch satellites. By every measure, it was a triumph. But there was a problem. A small one, embarrassingly small, actually. Mercury, the closest planet to the Sun, had a peculiar habit. Its orbit didn't quite follow Newton's predictions. Mercury's elliptical path around the Sun slowly rotated over time, a phenomenon astronomers called orbital precession. Most of it was explainable. The gravitational pull from other planets tugged at Mercury and nudged its path slightly. Newton's math accounted for all of that. But there was a stubborn leftover. 43 arcseconds per century. That's a rotation of less than half a degree over 100 years. So tiny it sounds absurd to lose sleep over. And yet, it was wrong. Newton's supposedly flawless theory couldn't explain it. Not even close. Then there was light. Astronomers had noticed that starlight passing close to the Sun seemed to bend very slightly, to curve around it, as though the Sun was somehow pulling at it. But light has no rest mass. Newton's gravity acts on things with mass. So what was doing the bending? Some scientists invented a phantom planet they called Vulcan, supposedly hiding near the Sun, trying to account for Mercury's stubborn precession. Others quietly fudged their calculations. None of it worked. None of it fit. The universe was trying to say something. The scientific establishment just didn't know how to listen. Then a 26-year-old patent clerk in Bern, Switzerland, a man who had failed to secure a single academic position after graduation, picked up a pencil and began rewriting the rules of reality. In 1905, Albert Einstein published 4 papers in a single year that shook physics to its foundations. One introduced the special theory of relativity, and it contained a claim so strange that most physicists initially didn't know what to do with it. The speed of light in a vacuum, Einstein said, is always constant. No matter how fast you're moving. No matter what direction. No matter the circumstance. Always exactly 299,792,458 meters per second. That doesn't sound alarming until you think carefully about what it implies. Speed is distance divided by time. If the speed of light never changes, but you change how fast you're moving relative to something else, then either distance must change, or time must change, or both. There is no other option. Einstein showed that time is not universal. 2 clocks moving at different speeds tick at different rates. A clock on a spacecraft traveling near the speed of light will tick more slowly than a clock sitting still on Earth. Not because something is wrong with the clock. Not because of vibration or interference. But because time itself is genuinely running slower for the moving traveler. This is called time dilation, and it is not a theory anymore. It has been measured directly with atomic clocks on aircraft and verified to extraordinary precision. That was Einstein's first revolution. But he wasn't finished. He spent the next 10 years wrestling with a much harder question. What does all of this mean for gravity? The key breakthrough came through a thought experiment, the most powerful tool Einstein ever used. He imagined himself inside a sealed elevator, falling freely through space. With no windows, no reference to the outside world, he would feel weightless. He would float. And critically, He realized he could not tell the difference between falling freely in a gravitational field and simply drifting through empty space far from any mass. The experience would be identical. Then he flipped it. If the elevator were instead accelerating upward, being pulled by a rocket, say, he would feel pressed to the floor. And again, he realized something extraordinary. He could not tell the difference between that upward acceleration and simply standing still on the surface of the Earth, feeling gravity pull him down. The two experiences are physically indistinguishable. Einstein called this the equivalence principle, and he later described the moment it struck him as the happiest thought of his life. Because if gravity and acceleration are the same thing, if you cannot tell them apart even in principle, then gravity must be something far more fundamental than Newton's invisible force. It had to be built into the very structure of space and time. Over the next decade, Einstein developed this intuition into a full mathematical framework. And the picture he arrived at was this. Space is not empty. Time is not separate. Together, they form a single four-dimensional fabric, what Einstein called spacetime. And mass warps that fabric. The more mass an object has, the more deeply it curves the spacetime around it. Picture a heavy bowling ball placed on a stretched rubber sheet. The sheet sags and curves around the ball. Now roll a marble nearby. The marble doesn't travel in a straight line, it curves toward the bowling ball, following the contours of the warped surface. From a distance, it looks like the bowling ball is pulling the marble. But it isn't. The marble is simply following the shape of the space it's traveling through. That is gravity. Not a force reaching across empty space, as Newton imagined, but the curvature of spacetime itself, caused by mass and energy, shaping the paths that everything, matter, light, even time, must follow. The physicist John Archibald Wheeler later summed it up in a single sentence. Mass tells spacetime how to curve, and spacetime tells mass how to move. In November 1915, Einstein published the complete general theory of relativity. 10 elegant equations describing precisely how mass and energy curve spacetime, and how that curvature governs all motion. And almost immediately, those equations did something Newton's never could. They calculated Mercury's orbital precession. All 43 arcseconds per century of it. Perfectly. No phantom planets. No fudge factors. The universe, once you understood that spacetime curves near the Sun, behaved exactly as predicted. But Einstein needed more than Mercury. He needed a test dramatic enough that the world could not ignore it. He got one in 1919, from the darkness of a total solar eclipse. British astronomer Arthur Eddington led 2 expeditions to photograph the solar eclipse of May 29th of that year. The eclipse would momentarily block the blinding light of the Sun, allowing scientists to photograph stars whose light had to travel close to the Sun's edge to reach us. If Einstein was right, gravity would bend that starlight and the stars would appear slightly shifted from their true positions. The amount of bending Einstein predicted was about twice what Newtonian physics would predict. When the photographs were analyzed, the stars were displaced by almost precisely the amount Einstein had calculated. Not Newton's amount. Einstein's. Overnight, Einstein became the most famous scientist on Earth. The headlines the next day were unlike anything science had produced before. A revolution had arrived. And it was only getting started. Hidden inside Einstein's equations, however, was something even he found deeply disturbing. A prediction so extreme, so seemingly impossible, that for decades physicists refused to take it seriously. The equations showed that if enough mass were concentrated into a small enough region of space, the curvature of spacetime wouldn't just become steep, it would become infinitely steep. A region from which nothing could ever escape. Not matter. Not energy. Not even light. A black hole. The mathematical possibility appeared almost immediately after Einstein published his theory. Just weeks later, a German physicist named Karl Schwarzschild, who was at that moment serving on the Eastern Front of World War I, derived an exact solution to Einstein's field equations. From the trenches, he mailed his calculations to Einstein. The solution described what we now call the Schwarzschild radius, the critical size to which any mass must be compressed in order for it to become a black hole. If you could compress Earth to the size of a marble, about 9 millimeters across, it would become a black hole. For the Sun, the radius is roughly 3 kilometers. Einstein read the paper and was deeply uncomfortable with the result. He believed some physical principle would prevent matter from ever actually collapsing that completely. He wrote a paper in 1939 attempting to argue that black holes could not form in nature. He was wrong. When a star 8 or more times the mass of our Sun exhausts its nuclear fuel, the outward pressure that had been balancing gravity for millions of years suddenly disappears. The star's core collapses in a fraction of a second, imploding under its own weight. If the remaining core is heavy enough, no known force in the universe can stop that collapse. Not the pressure between electrons. Not the pressure between neutrons. Nothing. The core collapses to a point of effectively infinite density, called a singularity, surrounded by a boundary called the event horizon, the point of no return. Cross the event horizon, and you are gone from the observable universe forever. You can never send a signal back. You can never escape. Even light, moving at nearly 300,000 kilometers per second, is pulled inward and cannot get out. But the effects of a black hole on the space around it are very much visible. Matter falling toward a black hole forms a swirling disk of superheated gas, an accretion disk, that can glow brighter than an entire galaxy. Jets of plasma are sometimes hurled outward from the poles at nearly the speed of light, stretching for hundreds of thousands of light years. And time itself, near the event horizon, runs extraordinarily slowly compared to clocks far away. This is not a metaphor. It is a direct mathematical consequence of Einstein's equations. An astronaut hovering just outside the event horizon of a black hole would experience time far more slowly than a person watching from a safe distance. For every hour the hovering astronaut experienced, years, or even decades, might pass for the distant observer. This is gravitational time dilation. And it has been measured and confirmed, in far milder forms, right here on Earth. Physicists also discovered that black holes don't come in just one size. Stellar mass black holes, formed from dying stars, range from a few to a few dozen solar masses. But lurking at the centers of most large galaxies, including our own Milky Way, are supermassive black holes, containing millions or even billions of times the mass of the Sun. The black hole at the center of our galaxy, called Sagittarius A star, weighs roughly 4 million solar masses and sits about 27,000 light-years from Earth. For most of the 20th century, these objects were inferred from their effects, never directly seen. Because how do you photograph something that emits no light? You photograph the shadow it casts. In 2017, an international collaboration of over 200 scientists from around the world activated 8 radio telescope observatories simultaneously, in Hawaii, Chile, Spain, Mexico, Arizona, and Antarctica. Using a technique called very long baseline interferometry, they synchronized these telescopes using atomic clocks accurate to within a fraction of a nanosecond, and combined their signals to create a virtual telescope effectively the size of the entire Earth. The data collected was staggering, so much that it could not be transmitted over the internet. Petabytes of hard drives were physically flown to processing centers in the United States and Germany, where the data was combined and processed over 2 years using algorithms developed in part by a young computer scientist named Katie Booman. Their first target was Messier 87, a massive elliptical galaxy 55 million light-years away, home to a supermassive black hole estimated to contain 6.5 billion times the mass of our Sun. On April 10, 2019, the Event Horizon Telescope collaboration released the result. For the first time in human history, the shadow of a black hole was visible. A glowing, asymmetric ring of superheated plasma surrounding a region of absolute darkness. The ring was brighter on one side, exactly as Einstein's equations had predicted, because matter on the side moving toward us is Doppler boosted, its light amplified by its motion in our direction. The size of the shadow. The shape of the ring. The asymmetry of the brightness. Every detail matched general relativity with extraordinary precision. Humanity was staring directly at warped space-time. A theory more than 100 years old, built by a man with chalk and paper and a profound refusal to accept that the universe was simple, had described the most extreme object in existence to within the margin of measurement error. Then, in May 2022, the collaboration released a second image, this time of Sagittarius A star, the black hole at the center of our own galaxy. Again, the image matched Einstein's predictions almost exactly. 107 years after the general theory of relativity was published, we had photographed the monsters it predicted. And they looked precisely as described. Here is something that might genuinely surprise you. Einstein's abstract, theoretical ideas are not locked away in physics textbooks and university seminars. They are woven into technology you use every single day. Your GPS would fail within hours without them. GPS satellites orbit Earth at about 20,000 kilometers altitude. At that height, they sit higher in Earth's gravitational well, which means, according to General Relativity, their clocks tick slightly faster than clocks on the ground, by about 45 microseconds per day. At the same time, those satellites are moving at roughly 14,000 kilometers per hour, which causes their clocks to tick slightly slower due to special relativistic time dilation, by about 7 microseconds per day. The net effect is that satellite clocks gain approximately 38 microseconds per day relative to clocks on the ground. 38 microseconds sounds negligible. It isn't. At the speed of light, 38 microseconds translates to roughly 11 kilometers of positional error every single day. Without corrections derived directly from Einstein's equations, GPS would accumulate errors of nearly 11 kilometers per day and become useless within hours. Every time you navigate anywhere, you are relying on the general theory of relativity. Gravitational lensing, another direct prediction of Einstein's curved spacetime, has become one of the most powerful tools in modern astronomy. When a massive galaxy cluster lies between us and something far beyond it, the cluster's gravity curves spacetime so dramatically that it acts like a lens, bending and magnifying the light from objects billions of light-years behind it. The result is that entire background galaxies are stretched into arcs, rings, and sometimes duplicated into multiple images. Astronomers now routinely use this effect to study the earliest galaxies in the universe and to map dark matter, invisible matter that can only be detected by its gravitational effect on light. Einstein's geometry has become our telescope. And then there are gravitational waves. In September 2015, the LIGO observatories in the United States detected something extraordinary. Two black holes, each roughly 30 times the mass of the Sun, had been spiraling toward each other for billions of years, 1.3 billion light-years away. In the final fraction of a second before they merged, they were orbiting each other 500 times per second. The energy released in that collision was greater than the combined light output of every star in the observable universe during that moment. And the impact sent a ripple through the fabric of space-time itself, a gravitational wave, spreading outward at the speed of light. By the time that ripple reached Earth, it had weakened to the point where it stretched and compressed the entire 4-kilometer arm of the LIGO detector by less than 1,000th of the diameter of a proton. That is a change in distance smaller than anything previously measured in human history. And they measured it. Einstein had predicted gravitational waves in 1916. They were finally confirmed 99 years later. He had been right again. So here is where we stand. A man who couldn't get an academic job, sitting in a patent office, asked what the universe would look like if you were riding alongside a beam of light. He followed that question, with nothing but mathematics and imagination, to a conclusion that bent space, slowed time, predicted invisible monsters at the hearts of galaxies, and described ripples in the fabric of reality itself. And then, one by one, over more than a century, every single prediction was confirmed. Black holes exist. Gravitational waves exist. Time genuinely slows near massive objects. Light genuinely bends around gravity. The universe is not a fixed, rigid stage. It is a dynamic, living geometry, curved and warped by everything in it, and curving and warping everything in turn. We know this not because we took it on faith. Not because it sounded beautiful, though it does. We know it because we tested it. Again and again and again. With atomic clocks. With radio telescopes linked across entire continents. With laser interferometers sensitive enough to measure a fraction of a proton's width. The universe has been giving us the same answer every single time. Einstein was right. And the terrifying part is, we still don't fully understand why the universe works this way. Which means the biggest discoveries in physics may still be ahead of us.